All right, guys. 1 second. I want to make sure it's muted. Yes. Today's topic is clustering. This is one of the many very important things we do in machine learning. So far, you have learned about classification and regression. In both of those algorithms, the goal was to predict something. For example, in regression, you predict a number. When we talked of the entrepreneur trying to open an ice cream shop on the beach, the input was all the weather data. The output that you were trying to predict is how much ice cream would the entrepreneur be able to sell on the beach. In the case of uh, classification, for example, you're trying to detect whether something is a cow or a duck. Right? It's a process of identification, and that identification, to the extent that you have, you're trying to tell which class it is. Categorical variable is the formal word you use. Is it a cow or a duck? Or more practically, whether to give this person a loan or not. How much is the risk? And based on that, you make a decision to give this person a loan. If you're a banker, to give this person a loan or not. And or as a friend, some friend comes by and says, I want to take give me a loan of 1 lakh rupees or something like that. And you would want to know whether it is safe to loan to this person, whether there's a reasonable chance of it's coming back. And if so, do you give him the loan or not? That's a classification problem, right? Or trying to, for example, if I show you a character, any character, and or some text, and you're trying to determine which of the languages the text belongs to. Is it in the Indian family of, let's say, North Indian family of languages, Devanagari script base? Is it one of the, for example, is it Tamil, or is it Tibetan, and so forth? So when you try to do that, you are again classifying. You're looking at the input, and you're trying to speak to or estimate which looks the most likely answer. That's classification. But nonetheless, in both these situations, the output is a prediction. There is an output. And in a sense, you're building a predictive model, a machine that can make predictions based on inputs, right? That generalizes from data, learns from data, generalizes from that to be able to make predictions on unseen data. This form of learning is called supervised learning. Supervised part being the training part where you learn from training data. We saw that in the lab for California housing. Today, we're going to deal with another area of machine learning altogether. Its purpose is not to make predictions. The purpose here is to just find interesting patterns in the data. When you discover these patterns, you learn something about the, the data and the forces that might have produced the data. Now, there are many things that you can recognize in a data pattern. The simplest of them is the cluster. You may find that data comes to you in not uniformly distributed in the feature space, but is clustered around some points in the feature space. It does happen. Now, the question is, how often does it happen? We'll come to that in a moment. But to the extent that there may be clustering of data, or the data may be bunched together in the feature space, it is an exercise to discover those clusters if they exist. A different kind of example of supervised learning could be you, unsupervised learning. So this is different. Pattern recognition could be, for example, you look at data and you build, you understand what people, mathematicians, use a technical word, a probability distribution, the probability distribution of the data in the feature space. If you can determine the probability distribution of the data quite clearly, it leads to a very powerful effect. You end up with a generative model. Now you can generate data at will. You can, what you have done is you have taken data, learned from it, and you have a generative model. You can go on generating new data. And these generative models these days are extremely effective. They are quite the sensation. For example, all of these things, I won't go into those algorithms like variational autoencoders and things like that. But at the end of it, what happens is that they often become powerful models that can generate new data, and they're uncannily good data. Sometimes the line between supervised and unsupervised learning gets blurred. For example, some models is hard to tell. They lean more towards supervised learning, and still they do pattern recognition or generative, or they build generative models and so forth. So there's a bit of a continuum between supervised, semi-supervised, and unsupervised learning, as the term goes. Um, so I tend to use different words. I tend to use the word predictive modelings, generative models, and pattern recognition, and things like that. Right? And examples of that is, for example, of the generative kind of models are like suppose you have a whole lot of pictures. I give you your picture, and suppose I take another reference picture. Um, let's say you take a picture of whosoever is the latest Indian film star. Could somebody give me a name? Somebody who's very popular these days.
Amitabh Asif.
Amitabh is still going strong, is it?
Yeah,
Goodness, isn't he a geriatric fellow? Doddering old age, not yet, huh? Okay. So let's take Amitabh Bachchan. He was a guy of our generation, my generation. I'm impressed that
yeah,
he's still going strong. Okay, so let's take Amitabh Bachchan. So suppose you take your reference face and Amitabh Bachchan's face. What we can do, what a generative model could do, is it could generate all sorts of faces in between you and Amitabh Bachchan that make you look progressively like Amitabh Bachchan, right? And those faces will be very, very realistic. You won't be able to tell that these are not real faces. So these are called fakes, the fake images. And the fake images are all the rage. You can have and you can do not just images, you can do videos and you can do audios. One of the videos I'll post to the our discussion, Slack discussion, is a video that was introduced in the MIT machine learning course. It is of a president of United States, President Obama, who is very popular in US, despite the fact that he is no more the president, giving a speech. The entire speech was never given by Obama, but you can't tell that because it is generated by it is machine learning that's producing that. You can have a situation in which you are speaking, but you can have every word that you speak come out of the mouth of Amitabh Bachchan with Amitabh Bachchan's expression, with his accent, right? And you will never be able, it's very, very hard, actually, near impossible to tell that it is not Amitabh Bachchan speaking of what you are speaking. Okay. So that is the power and, of course, the danger of generative models. These days, it's become a huge issue. With power comes abuse, and it is being abused these days. So people create all sorts of fake images and fake videos and so on and so forth. These are called deep fakes. They are so utterly realistic that even machine learning algorithms, powerful machine learning algorithms, cannot tell the difference between them and reality. Right? So it's a completely different world we are entering. And so after doing the predictive models, I thought it was time for us to get into this other two kinds of models, generatives and the pattern recognition. But today, I'll start with um, obviously just clustering. There's a third form of pattern recognition. I mean, some more of them. There are many, many things in this space, but I'll talk about one more thing. This is dimensionality reduction. Sometimes, you get a lot of features. People are trying to determine, for example, factors that cause diabetes. Right. So you may get all sorts of factors, environmental and life science and genetic factors. Each of them is very responsible for diabetes to a different extent. But then let's take one class of people, type 2 diabetes, that is an adult onset diabetes. And the question is, which action that you can take will lead to the person getting or managing his or her diabetes better. So towards this end, you may think of, okay, uh, there's so many things a person can do. The person can, for example, go for a walk. The person can do, I don't know, pranayam. The person can do reduce the portion sizes of food, eat less sugar, and so many, many factors you can do. And you can enumerate the factors. There are hundreds of actions that can do. Each of them, in small measures, will benefit the person. Right? So when you try to make a recommendation or think about what will help this diabetic, you may be inclined to give a very complicated recommendation. But what you can do instead is look at the underlying theme behind those recommendations. And so let us say that plausibly you come to the theme that you tell the patient a thing more abstract. You don't give an action, but you instead say, do two things, or let's say three things. First, increase your activity level, do more physical activity, walk more, sweat for at least half an hour. Right? Whatever way you do it, whether walking, swimming, running, jogging, tennis, or whatsoever, just make sure that you have about half an hour of sweating in the process. Vigorous exercise in whatever form you like, and you should cut down your portion sizes in your sugar by a significant amount. Don't exceed this threshold. Right? And you can give up probably a third advice and say, make sure that you sleep at least 8 hours a day, 8 hours a night. And then, and you have derived these recommendations by looking at the data. But now you're making recommendations along only three axes: exercise, certain amount of exercise, certain amount of diet control, and a certain amount of necessary sleep, which is a far better thing to do. It goes to the core of the issue, lifestyle issues, compared to making small recommendations or very specific recommendations that you must walk and you must swim and you must do this and you must do that. But some of which may not be feasible. For example, if you look for swimming, there may not be a pond or a swimming pool nearby for the person. So, or a sea nearby. So, in a sense, what you're saying is get to the heart of the issue. And in some sense, the core factors, the underlying latent factors that are behind this feature, you can discover somehow, and they are fewer in number. So while there are multitudes of factors affecting an outcome, affecting a certain behavior, a certain data set, underneath them all are some few core latent. The word latent is a Latin for hidden factors, hidden factors. And those few factors are the real things you should go after. To do so, to discover those sorts of factors is called dimensionality reduction. Now, the literature of machine learning has a lot of techniques, beautiful techniques to do dimensionality reduction. It has a lot of techniques and vast amount of literature for generative models. It also has a lot of literature to discover clusters in data. Each of these are vast fields. Each of them with have produced like quite literally tens of thousands of PhDs, right? And researchers are working on those areas. So these are worlds in themselves, and machine learning is now a vast, vast field, as probably you must be getting a sense of. Right? It is as big as the field of medicine, say, or any other discipline, vast discipline. So, but today we can't get introduced to all of that, and we are going to take an hour, hour and a half. We will focus on one thing, which is the detection of clusters in data. This process is often called clustering, and the algorithms that find clusters are called clusters. So let us start with the very basic principles, and I'm going to do that now. Uh, we'll walk our way through, right, and walk our way through this whole process. Let us do that. So suppose you have data. I'll take an example. Uh, let's go back to the example that I keep quoting. Let's say cows and ducks. Suppose you look at the weight of the cow and the size of or the animal and the size of the animal, you would agree that all the ducks are lightweight. So let's say that this is x1 and this is x2, the size. And then, so would you agree that most of the ducks data would be clustered here because they are small and lightweight creatures. They're flying, they're birds, right? Whereas the cows are big and heavy, so they will be clustered somewhere around here. So, folks, is this looking pretty obvious? Right? If you look in the world, this particular feature space, which in this case is a two-dimensional feature space, I hope it is very obvious that you should observe some behavior. A data distribution would look like this, right? So far, so good, guys, right?
Yes.
Yeah, simple. It's a simple fact that you would observe something like that. Obviously, I'm sort of, I'm not, I don't have actual weight and duck data with me. I mean, sort of weight and size data for cows and ducks with me. So, but I'm sort of giving a motivating example, and I hope reality is not too far from this. Now, what you observe is that you have in the data clusters. This is a cluster, and this is a cluster. Now, the question is, how do you discover clusters in the data? Right? So the human eye, of course, will immediately notice the cluster. The human eye and the human brain is the most fantastic computational and machine and a learning engine. Right? If you were to think of it as a learning machine, it is the most amazing learning machine that we have. And not just humans, if you go and look at your or any of the animal species, vision is one of the greatest marvels in the animal kingdom, isn't it? I don't know about plants, but certainly in the animal kingdom, vision develops pretty early, from very rudimentary forms of visions, which may be just sensory, to full-blown vision. And someone once, I read from a researcher once that the vision evolved close to 100 to 300 million years ago in the species, in the evolution of animals. So what has happened is, if you think from a machine learning sense, the brain as a machine and the eyes as learning machines, these machines have had absorbed data that spans close to 100 to, I don't know, I'll just use the word 100 million, in the order of 100 million, in the order of 100 million years, right? So it has been learning and looking at data for 100 million years. The end result of that is the the learning that has come from that is so super efficient that when we look at a picture like this, the human eye recognizes the clusters, perhaps even before you utter the word cluster. Right? It has seen it just in the blink of an eye, it has seen it. Instant, it sees it. But the question then arises that that is fine for the human eye, but can a machine detect it? Can you write code that will detect clusters in data? So there has been a lot of effort in this and a lot of history. See, when you look for clusters in data, if you really think in a naive way, you can say, well, if I have programming background, I can search for things, I can sort data. Why can't I discover clusters in data? It must be easy. But no matter what you do or how you try, you will soon realize that the the straightforward programming cannot solve this problem. We know today that this problem is at least NP hard, right? Or maybe NP complete, in the sense that programs cannot do it in non-polynomial times. And yet, the human eye or any animal eye detects the presence of clusters immediately, right? So, if you have a lion and you show a herd of ducks, a herd of cows, it wouldn't take the lion more than a blink of an eye to see the herd of cows and start running towards it. Right? So there is no ambiguity in the minds of the lions. So we do know that clusters can be discovered somehow. The question is how, and that's where machine learning comes in. Machine learning looks at this problem, and the answer is, you know what? There is a reason why you can't discover clusters immediately. Is it has to do with the definition of the clusters. Like for example, is this red thing the cluster, or is this more dense area inside that is the cluster? You see the ambiguity. If you look at the dense area that I have, where I have perhaps more points, so which of these would you call the cluster? There is an interpretational aspect to it. There is also an aspect of granularity. At what level do you want to see the cluster? Do you want to go even further? And let us say that you have points very close here. Do you want to go further and call this little thing the cluster, right? So what is a cluster? Where, yeah, and what notions do you need to define a cluster? Those issues come up. And you have to address those issues, then only you can discover clusters, which is why it is not a problem in normal programming. It is a machine learning problem. Are we together? But okay, so this is about the process of discovering clusters. But even before we go here, there is an outstanding problem. Given data, do you expect to see clusters? How often would you find clusters in data? Suppose you imagine that you're taking a broad sweep and surveying all sorts of data sets that you have been given, that you find something coming from mechanical engineering and aeroplane flying, some medical data, some financial data, some all sorts of data, your bugs, your econometric data, social psychology data, everything that you can consider, right? Uh, there's a wide variety of data in the world, of course, and an infinite amount of data sets that one can have. It is a question worth asking. How often would we find clusters in this data? So let me throw that problem to you. If I were to ask you, in your just gut feel, what proportion of those data will have the presence of clusters? 1%, half a percent, 0.1, 1 in 1,000, 1 in 10,000, or something like that. Let's see what our gut feeling says. Would somebody like to answer? Speak up, guys. Speak up. Anybody still listening?
Yes, sir.
Yes, so make a guess.
Yes, 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 sir.
Yeah, so throw a guess, guys, throw a guess. You'll probably see it one in thousand, one in hundred. How often would you see the presence of clusters in data?
So 1 in 1,000?
One in thousand. That's a thank you for stepping forward and making a guess, Manasa. Anybody else? Um, except for the repeat students, of course. Anybody else? How often do you think you'll see it? Let me start taking names since you guys are not stepping forward. Rahul?
Uh, yes, sir. It's like uh, in 100, we usually see the cluster data.
How many times in 100? One in
Uh,
100, is it?
yeah, 1 in 100.
Mm. Anybody else who'd likes to have a different answer? What about you, Shrikant?
1 in 1,000.
One in thousand. And what about you, Kumar?
Same, sir. 1 in 1,000.
One in thousand. All right. So, Rajeshwari?
I think she just joined.
Yeah, sir. Hello.
Yes, go ahead, Rajeshwari.
Yeah, no, sir. I just joined due to network issues, so that's it.
No problem. How about you,
Did I miss anything?
Suresh?
See,
How?
we always, yes, if we always see a cluster. So I don't know how one in 1,000 or 1 in 100, how much that would be a realistic, but we always see a cluster in the given data.
That's right. Did you attend a previous lecture of mine on this? I think you did, isn't it? I've talked about this.
No,
Or is it your speaking
no,
experience?
no, I didn't attend any session.
Then it's a very good answer, actually. Surprisingly, it turns out that you very often see a cluster. I would say that clustering in data if is all like greater than 80 to 90% of the time. If you have data, you're much more likely, even more, I would say that 95% of the time, you always have clusters in the data. And more than even 95 would be actually, now the more I think about it in the examples, it's very rarely do you see an absence of clusters. And the reasons are quite interesting, actually. It has to do, I mean, I could argue from a theory called the chaos theory or nonlinear dynamics, but I'll explain it in a simpler way. See, have you ever gone to a wedding reception in India? Those are big events. When you go there, suppose you're looking from the balcony to people in the sort of the room, the main room where all the guests are sitting. Do you see the guests uniformly distributed or do you see them in clusters? Do they
Form.
Clusters.
form clusters?
Clusters.
Isn't it? Naturally, they sort of congregate into small groups and talk and things like that, and they're forming. You go and look at a schoolyard. Do you see children just randomly distributed everywhere, uniformly distributed, or you see them in little bunches, little clusters or groups? You always see them in groups, right? You stand on a highway, now you have highways in Bangalore and in India. So you stand on a it is called an overpass. Do you have overpasses over your highway? Like, can you stand on a bridge over the highway and look down at traffic flowing?
Yes, sir.
Yeah.
If you ever do that, you will observe something quite interesting. Even when there is no traffic congestion, especially when there is no traffic congestion, when the traffic is congested, there are no clusters. It's one uniform sea of cars and automobiles stuck and motorcycles and everything stuck there. On the other hand, when the traffic is free flowing, there is no congestion. If you stand on such a bridge, an overpass, and you look at the traffic flowing, you will observe that the cars don't, or the automobiles, they are not growing uniformly separated out, or more or less uniformly separated out. They sort of come in bunches, they come in waves, right? One big wave of cars and automobiles will go, followed by a little gap, and then more automobiles will come. And it is worth wondering. So what is happening is that on the highway, they are clustered. They're going in little bunches together. Whereas ideally, they should perhaps be uniformly spaced out, right? It doesn't happen for some reason. It leads to, and the reasons are to do with nonlinear dynamics and chaos theory and things like that. It's very interesting that it happens. More than that, if you just look at something very basic, look at the mails coming from, the postal mails coming from your coming to your house, or sometimes the packages coming to your house and so forth, you will realize that someday you don't get much mail, one or two mails. Some days it seems that the whole world is remembering you, right? You get a lot of mails, but you don't get a steady state of mail. It isn't that every day you'll get exactly 3 mails, the average number of mail to your postal, envelopes to your house. Have you noticed this, guys, that some days you get much more and some days you get much less? Okay. Now, when you think about it, each of these letters are coming from completely independent sources. They are not in collusion. And yet, coming from completely independent sources, nonetheless, when they reach you in bunches, right? They reach you in clusters and clustered in time, right? A lot of them come on one day, another day that you wouldn't get as much, and so on and so forth. So they come in waves. Right? So when you look around everywhere, you will see that actually data is clustered. Things, events, happenings are clustered. Are we getting the sense? Right? There was a very interesting thing you can do. Even if you make people, like let's say, enter a room. I'll take this thing. And this is coming from one of the first episodes of a lovely TV show, which I encourage you all to see. One of the few TV shows which are centered around machine learning. It is called Numbers. B. The 3 is reversed, I believe. Numbers, right? It may be visible in Netflix, I think. I hope so. Or in one of these streaming services that you folks have in India. Check it out. It's an old TV show, but I think it's still very good because each episode introduces. It's a mystery. There'll typically be murder mystery or something or the other. But the solution of that will come through machine learning, through the application of mathematics to the problem. So one of the first episode had something similar to this. The mathematician was trying to show that data is clustered. And when data is not clustered, it means somebody is deliberately trying very hard to prevent a pattern from being visible. Right? So what he gave as an experiment, he asked everybody to enter a room and stand somewhere. Right? And when they stood somewhere, they automatically began to form clusters. Right? They were not uniformly spread all over the room. Right? It is natural for data, for people, for everything to form clusters. So an absence of clusters usually shows something unusual. There are absences of clusters. For example, if you go to the beach and you look at it, all you'll find is sand. Right. Now you may say that sand too is clustered in some sense, but sand is more uniform. You probably wouldn't see very well-defined clusters. But between the sand, you may find clusters of bushes, right? Some green bush or something like that. But the sand itself is more or less through a lot of erosion and so forth in the sea activity. It has become a uniform bed of sand. Right? So there are situations where you don't see clustering of data, but much more, it is much more likely that you will see that. And to me, the most evocative proof of this is to just lie down on summer days and look up at the sky. I don't know if it is still true in India, but when I was growing up, that was 30 years ago, 30, 40 years, actually 40 years ago, uh, we, it was common in India because load shedding used to be common, or because in India, the houses get extremely hot in summer. You don't feel like sleeping indoors. You didn't in those days. So you would sleep outdoors. When you would sleep outdoors, you would be, look sleeping in your courtyard, or you'll be sleeping on the roof, and you'll be looking up at the sky. When you look up at the sky in the night, what do you notice? You see stars there. Now, are the stars uniformly distributed? Like, do you see a sky filled with random and uniform distribution of stars? You don't see that. What do you see? Anybody?
Clusters of stars.
Yes, the stars are clustered, right? And especially if you have a telescope, it becomes much more apparent. We have galaxies, then we have constellations of galaxies. And the universe is not a uniform distribution of stars, isn't it? So that's again an evidence of clustering. So these are all just to give you a variety of data that exhibits clustering. So clustering is a fact. Therefore, the question remains, though, how do we discover those clusters? And that is the context of today's algorithms. The clustering, people all call these the clustering algorithms, or they often also call them, so the words that people use are clustering algorithms, or clusters. You will see clustering algorithms much more commonly used. Clusterers is more intuitive, right? But I suppose it's less commonly used. And actually, you find clusters used paradoxically in more formal literature. So research papers and so forth, you'll see the word cluster mentioned. Anyway, so today we are going to learn three kinds of clusters in quick succession. We will learn about partition-based, and I'll just call it, okay, let me take the example, k-means. We will do hierarchical, and we will do density-based. So today would be a bit of a long session because we'll give some time to doing each of them. It may perhaps be the longest of the sessions we have done. So if you feel that we are going too long, we can of course break it up into parts and do the second part next time. Okay? So I will start with the first one, which is the simplest of them. And the most ubiquitous, any way you look, you'll find somebody or the other has applied k-means clustering. Its strength is that it is simple. Its weakness is that it can be unstable, and it may create clusters which are unrealistic. Right? Those are its limitations. Now, k-means, the version that I'm going to explain here, it is a very simple version. Usually you use a bit more sophisticated version of it to speed it up, to make it run faster. But we don't want to get into the complications. We want to get to the core of the idea. And to get to the core of the idea, we will avoid all sorts of optimizations. So for those of you who are technically inclined, you will see that you use data structures like metrics, like certain things like metric spaces and metric trees, and KD's sort of KD tree is quite common, right? And so forth, cover spaces, O trees, O ball trees, and so on and so on. There are all sorts of data structures that people do bring into the space, but I won't go and talk about all of that because it would be a distraction from the core idea itself that we will use. Right? So let us go back and bring back the problem of our cows and ducks. So suppose you have data point again, and I'll just make this ducks here. And then ducks, and then there's cows. So this algorithm, what basically says is that it solves half the problem. See, with clustering, there are two main problems to solve. Clustering has two parts. A, how many clusters are there? B, right, where are the clusters? So discover the clusters. First is decide how many clusters are there. Find out how many clusters are there. Now, when you look at this diagram in the feature space, which is X belongs to here, it's a two-dimensional plane. And I'll just keep it abstract instead of weight and size, but you can think of weight and size as as a motivating example. When you look at this, I ask you, how many clusters do you see?
2, sir.
Two clusters, right? So now k-means does not answer the question how many clusters. It says you tell me how many clusters to find, and I will find you those many clusters no matter what. So for example, if you ask it to find 10 clusters, it will go find 10 clusters in this data. So it leaves half the problem to you and solves only the other half, the part B of the problem of the thing. It says, tell me how many clusters you want to see. So let's say that you make the happy guess of 2 clusters. So that is what the K stands for. K is equal to number of clusters. So let us say that you say K is equal to 2. How will we do it? Let's figure it out. Now, so I'll explain the word means here. That is where it will come to. So the way you do that is, it is made up of a few steps. And these are very sort of intuitive steps. It says, first, step 1, pick any 2 points randomly as the initial centroid. Centroid means center of gravity. Right? Pick any 2 points. So let us say that you pick, and of course I'm getting to the intuition first. So let us pick some point that is like, which one should I pick? Let's say if you pick randomly, you ended up picking this point, right? And also randomly, let us say you end up picking which point? Maybe this point. These are 2 random points that you picked up, right? So then let me just call it 1 and 2, the second point. Then the algorithm says 1, 2, assign every point to the nearest centroid. Here, initially you said centroids are 1, 2. So if you take every point, so for example, if I were to take this point, which centroid is it closer to? Is it closer to 1 or is it closer to 2?
1.
1, right? So you say it belongs to 1. So in other words, every point votes or becomes the constituency of one of these 2 centroids. When you have done this, you would agree that the entire data set would have bifurcated into 2 sets, one belonging to centroid 1, the other belonging to the other centroid, isn't it? So, so with that being true, would you agree that all these points would belong here, and all these points would begin to belong to centroid 2? Does that make sense, guys?
Yes, sir.
Then it says that the algorithm basically says that, aha, that's pretty lovely, and you're pretty much done. The third step is find the centroid. And so when you assign each point to the nearest centroids, i.e. build the 2 clusters, right? Build the 2 you build the two clusters. Now, the third step is find the centroid of each cluster. So if you look at the centroid, what is centroid of a cluster? The center of gravity, the center of mass, or the center, Basically, it is the central, the mean point, the mean value of x1 and the mean value of x2. Of x1, x2 for each cluster. So if I look at this picture, let us draw the mean. Would it be fair to say that the mean would be, let's say, somewhere here? This is the mean or the center of gravity or the center of this cluster. And the mean of this perhaps is somewhere here. Would that be reasonable? Guys?
Yes, sir.
It would be reasonable. So what happens is that you call these the new centroids. Find the centroids of each cluster, and these become the new centroid, right? And then what you do, and here is the part that is interesting, you keep repeating this cycle between 2 and 3, right? The two-step part, first assign all the points to the nearest centroid, and then find the centroid for each of the clusters. You keep doing this, do this, repeat till you feel like stopping. Well, that's a very vague word to use, feel like stopping. Machines don't feel, but I'm just using an intuitive word, feel like stopping. For example, you can have many stop criteria. Stop criteria could be criterion could be one, the centroids are not moving. Do not move much. Or it could be that points are, very few points are changing loyalties, like very few points are moving from one centroid to another, right? From one centroid, from one cluster, I should say, perhaps, from one cluster to another. Are we together? Right. So, or you could do, or just arbitrarily pick a number, or arbitrarily, this is butchering the spelling, arbitrarily pick the number of iterations. If you're pretty sure how long it will take, right? Iterations is equal to, I mean, whatever. You can say 5, 10, whatever suits you. And now you say, well, if you pick the number of iterations, what if you're not done? It is possible. Generally, k-means class converges very fast. Like, for example, in this case, you went from this to this, and from a random guess to the correct answer, quite literally in one step. Isn't it, guys? If you repeat it, you're not going to change your position or your clusters very much. So this is a happy example where the data is clean. Your initial guesses were good, right? And because your initial guesses were good, you quickly move to the centroid. Now, there is another, but it may not be true. Let us now look at the same data, but with bad guesses and see if it still works. So suppose I take this, I'll redraw this cluster, this diagram, and see what happens if the data is not what we think it is. Or I mean, data is what data, of course, I apologize. But the initial guesses are terrible. That's we are really unfortunate in making the initial guesses. So this is, I hope, a close approximation to the original data. Suppose you have this. Okay, this is Suppose you were unlucky and your initial guess was, just by misfortune, happens to be, let us say, these 2 points, 1 and 2. Well, now what? You realize that you have a problem here. These two are very close to each other as guesses. The question, therefore, is, will this work? Right? Let's find out whether it works or not. So what we again do is we associate all of these to its points. When you do that, you will initially discover that your first cluster is like this. These points will belong to one cluster, and these points will belong to the second cluster. Can you see that? If you assign all the points to the nearest centroid, given 1 and 2 as the initial guess of centroid, this is the cluster you'll come up with. Does this make sense, guys?
Yes, sir.
Right? You agree with that? So now comes the next thing. Let's find the centroid of the second cluster. The centroid of the second cluster would be the center of gravity here. Would it be reasonable to say that it will be somewhere here? 2? Guys, is that reasonable?
Yes, sir.
Yeah, that would be reasonable. Now comes the tricky part. For 1, where would it be? Would it be reasonable to say that the centroid would be maybe in this empty space somewhere here as a guess? Would this be a reasonable answer, guys?
Yeah, but that looks reasonable, but we don't have any data points there. No?
That is right. We don't have any data points, but that's perfectly okay. Our algorithm didn't say that you can't put the centroid where there's no point. Okay? This is one of the things we allow for. It looks very odd. The most empty space we are calling a centroid, but so be it. We do that, right? So this is the second step. Now let's use a different color. Let's make the now that the centroid has moved here, let us redo this. Let's redo the clusters. So it is clear that let's say that this point, if you let's make the cluster for 2, you would agree that most of these points would have gone to 2, and most of these, the rest of these points and all of this would go to 1. Are we together, guys? So the journey has been, the centroid has moved, the 2 has moved to this, 1 has moved to this, and now the pink or red color, whatever this is your new clusters, the 2 new clusters. So far, so good, guys?
Here actually the 1 can move to either to the second centroid, or it can come even to the first centroid. No, sir. There will be a 2 option for that in that case, because in the first group, so we have taken the complete thing, so which is it can come to both the centroid. I feel I don't know. I just guessing.
No. See, the center of gravity is the mean of points, no? The location of points. So in the beginning, you have a lot of points here and a lot of points here. So so let me just call this ducks, right? This was the ducks, let us say, and these were the cows. You cannot have one move all the way to the ducks in one step, right? In the beginning, because see, look at this, yellow points, you started very close to each other. So in the beginning, the yellow one will end up owning half the cows. And right, but it will own all the ducks, all the cows and half the cows and all the ducks. But then what happens is when you find the centroid, 1 moves to this pink colored one, right? The centroid is now here. Manasa, are you getting that?
Sir, actually no, sir. So actually, what you explained is like no, I don't know whether I'm correct. So here the centroid for the first one is the one which you have mentioned in the yellow color. I mean the one. So because both the things are close to each other, so the first centroid can be either to the one which you have placed in the center, and it can either be to the one which is next to it only. It can be both, right? So it cannot be only to one, I guess.
Okay, let us redraw. Let us redo the entire thing over again. Huh? I'll erase this and I'll redo the whole thing. Let me see if I can redo the whole thing. Suppose you take these two. Unfortunately, these two are your initial guesses. Centroid guesses. So this is an unfortunate pick because, of course, if you look with your eyes, they look as bad a choice as they can be, isn't it? But our rule is we still have to give the points to one. Every point has to belong to one centroid or the other. So let us take this point where my mouse is. Which centroid do you think that belongs to, this point? Let me just call it A. Where does A belong to? Which centroid does it belong to? One or two?
Two.
What about this point? The one very close to it where my mouse is. This belongs to? Two. So how about this guy? It belongs to?
Two.
It also belongs to two. But what about, so let me just call this C. What about this point? D. Which centroid does this belong to?
One.
One, exactly. So you have switched over. So how do you decide who belongs to that? One easy way geometrically is to take the perpendicular bisector of the line connecting to these two centroids, take the perpendicular bisector, and you would realize that everything to the left of this line belongs to one, and everything to the right of this line belongs to two. Would you agree? So for example, if you take this point, which is it likely to be closer to? It's closer to one, isn't it? Than to two. Right? So suppose you look at this point E. Which cluster does it belong? Which centroid does it belong to?
One.
One, right? And continuing that argument forward, here is your perpendicular bisector. All of these points, these dot points, which cluster do they belong to? Which centroid do they belong to? One or two? Which are they closer to?
One.
One. Manasa, are you agreeing with that?
Yes, sir. Now I got it.
Now you got it, right? And so the first time around, your cluster would be, your cluster would be something like this. Let me bring back those white points. Your cluster would be something like this thing. This entire thing is your cluster. One cluster, even though it has a lot of empty space. And this part is the other cluster, right? Now, what is the center? So now I'll remove this ABCD. Maybe they're cluttered. Maybe I'll leave it. Let's leave it there. Now ask this question of the centroid 2 and the cluster 2. So let me just give it a name, cluster 2, and this is cluster 1. Tell me, where is the centroid for cluster 2? Would you agree that the centroid for cluster 2 would be somewhere around this point? Is that where the center of gravity of those points are? Does this look reasonable, guys?
Yes, sir.
Yeah. So 2 has moved here. What about the centroid for 1? The cluster 1 owns half the cows and all the ducks. So far, cluster 1 is a rather rich farmer, has a lot of cows and all the ducks. Cluster 2 has only half the cows. So now where's the center of gravity of cluster 1? The centroid, where would you put it? Would you say
In
that,
the middle.
yeah, somewhere here? Let's say that it's somewhere here, right? Would it be reasonable to put it here?
Yes, sir.
Yeah. So now that it is here, let us repeat the process. Let us assign all the points to one cluster or the other. So we realize that when all the ducks will certainly go back to 1, they will remain with 1. What about 2? In 2, you will see that loyalties of some cows are changing, right? What will happen is, if I look at the perpendicular bisector of this, the perpendicular bisector is going along this line, right? So now these many cows all belong to 2. More cows now belong to 2. Do you see that? Some extra cows flipped over loyalty to 2. And these many, this is the cluster for, let me just call it cluster 1. And this is cluster 2. Are we together, guys? Would you agree with this? Right? Just look. So what do you notice? That cluster 2 is picking up points. Cluster 1 is losing the cows. What now? Let's go over to the, let me use another color now. I'll use blue, let's say. Let us find the centroid of 2, cluster 2. The centroid of cluster 2 perhaps could be this point. Would it be reasonable to say that?
Yes, sir.
Yes.
So this is 2. And what about the centroid of 1? Would you agree that it would have shifted to
Near duck.
near this? This is 1, isn't it? And now once again, you find the cluster for 2, right? So when you do the cluster for 2, let's join the 2 with a line and do a perpendicular bisector here. And you realize that what happens now, 2 ends up owning all the cows. Do you notice? Now 2 owns all the cows. Would you agree?
Yes,
Yes.
sir.
And 1 ends up, actually it owns this empty space also, but I won't focus on that. It ends up uh, owning all the ducks at the bottom. So this now is your, where am I? This is now your cluster 1, and this is now your cluster 2. Hmm. And now let's find the center of gravity of, let me use one more color. What could be it? Maybe green. I'll take green. Huh? Let's see, green, this is it. Okay, so now what is the center of gravity of this? It would be this. Would you agree that this is the center of gravity of 1? And the center of gravity of this cluster is perhaps somewhere here, or somewhere here, 2. Does this look reasonable, guys?
Yes.
Yes, sir.
And you know that you're pretty much reaching the end. Those clusteroids, now the points will not be changing loyalties, right? They will all stay within the cluster. And so the center of gravity in the next, or the centroid in the next iteration, is not likely to move. And therefore you have detected the clusters. You can say, I can stop now. I have 2 clusters, and my clusters are these clusters here and the clusters here. These are my final clusters, right? This region is 1 cluster, and this region is my other cluster. Right? That's how you do it. Or actually, more precisely, what it does is it also divides the empty space. So I join these 2 lines between the 2. I will have a perpendicular bisector. So you would say that everything on this side, though we don't, even though there are no points, like logically speaking, we are doing something like this. We are dividing the space into 2 parts. One belongs to cows and one belongs to ducks. Right. That is why these algorithms are also called space partitioning feature space partitioning algorithms. People don't use the word features prefix so often. Partitioning algorithms. K-means. K-means is an algorithm that clusters by dividing the feature space into regions. One region for cows and one for ducks. Are we together here? So it's a beautiful. The K-means is a very simple and elegant argument for finding clusters in data. You notice that even when you make very unfortunate choices, you can still discover the clusters, isn't it? You have a journey, points move. For example, if you look at the movement of one moved from here to here to here, and from here to here. Right? You see how it migrated, the centroid of one migrated. The centroid of two didn't migrate that much. It went from here to where? To here, and from here to here, and from here to here. Not much movement in two. But centroid one moved quite a bit. But at the end of the day, you settle down at a point at which the centroids have been discovered. So that is the power or the beauty of K-means. Now, there are a few limitations. One is, do you notice that if you make bad choices, it takes more number of times to find the answer, isn't it? For example, in the first one, where we made good choices of the good guesses of the centroids in the beginning, we converged much faster. On the other hand, when we made not so good guesses, it took a while for us to converge to the centroids. Right? So the runtime of your algorithm therefore becomes proportional to a random process, random choice of guesses. That's one limitation. There is another limitation which is pretty actually bad, which is, and I won't go into that. Sometimes you end up with centroid choices in the beginning, guesses so bad that it ends up sitting on the perpendicular bisector of the real clusters. And so, as you can argue, if you're in the perpendicular bisector, you just get to a very unstable situation in which the clusters that you discovered are bad clusters. They're not good clusters. So for example, if you end up discovering a cluster halfway like this is one cluster and this is another cluster, the lower part, right? Now, what happens is when you do that, your cluster centroids don't move. In both the cases, the centroids would be somewhere like here and here, right? So this will become like 1 and 2 in that situation. And when it becomes that, there is no further movement, but those centroids, as you can see, they are terrible, right? They hardly, I mean, those clusters are not real clusters. Just one look at it and will tell you that this somehow is not right, right? You have picked up half of one cluster and half of another in one cluster, right? And in the second cluster also, you have done the same thing. So these cause instabilities, and so people have found ways to solve this problem. Many clever ways people have found. So one clever way they can argue is, so I'll just erase this part. These bad clusters that I drew. Let me just erase it. Okay. So one way that you can do is whenever, or maybe I'll do it in the next part here. So let me draw this again. I think the previous drawings have become cluttered. Suppose I have this, again, I draw these points. And I draw these points here. And so let us say that I randomly pick a point, let's say somewhere. Let's say that I pick this point as one. One suggestion that often helps is pick the second point, which is as far away from the first point as possible. So what would that be? It cannot be one of the ducks. You'll end up picking maybe a cow. This one will become your 2. Would you agree? This seems to be the furthest point This cow seems to be the furthest point from 1. Would you agree with this?
Yes.
So then what happens is, as you can imagine, that this will converge very fast, because in one hop, you will end up declaring this, let me use the same color. You will end up using this as your first cluster, and this was a point, and this as your second cluster. And then in one hop, you would get to the right answer, which is that 1 will move to this guy and 2 will move to this guy, and the clusters will remain the same. Do you notice this? Right? So it's a clever trick. You can, sometimes it works, it doesn't always work. Sometimes it works. There's no guarantee that this process itself will work. Right? But it does seem to work quite often. And sometimes people use this. Then sometimes people will do other tricks. Like, for example, they'll say, you know what? I need a way to measure the quality of a cluster, how good the clusters are. And so there are mathematical measures. One of them is called within cluster sum squared distance. What it means is, suppose you're given points, 4 points, right? Or 5 points. How many? Or did I make 6 points? Find every pairwise sort of a relationship. I don't know. Did I miss something? I'm sure I missed something. Yeah, missed this. Missed this. So you see, you have a lot of interconnections between the 6 points. For each of them, find the distance. Let me say D1, D2, all of these distances. And take the average, or take the within square, some square distances, just add D1 squared plus D2 squared, etc., etc. And sometimes you take the average, you divide it by total number of points, let's say 1/6. Right? So you take these distances between all the points. And then what you find is, and do it for the other cluster also. So it's a summation in mathematical notation. It will be a summation over each of the clusters, and it will be a summation over every pair of points, distance between every pair of points, Dij, belonging to a particular cluster, square, Dij squared, belonging to whichever cluster it belongs to. You do that. Why is this important? The reason it's important is, suppose you make the mistake and you pick, suppose the points are here. Let me just make a few points, not too many points, to illustrate this. Suppose your points are here. I'll deliberately put them in a line for the time being. Let's say like this. A little bit like this. Suppose you made bad clusters. Suppose you discovered clusters like this and this. So let's look at the cluster 1. You would notice that if I try to do paired distances between every 2 points in the cluster, you will end up with these big lines. Do you notice that? How many long, big lines I'm drawing compared to the other one? And we can keep going that. So you realize that these lines are much, much longer than in this situation when the clusters are clean. So your WSS here will be large, right? And so if what you do is you pick the WSS cluster, minimize WSS. How can you minimize WSS? What you do is you keep on doing the clustering a few times. Let's say that you do 10 tries. So you build 10 random clusters, and then you pick the minimum WSS. Now in practice, what will happen is the probability that you'll make a blunder like this is very, very low. So what will happen is at least 9 times out of 10, you will pick the right clusters. So 9 values will be very close to each other, and the 10th value may be off if you're unlucky. right? It is very, very, very unlikely that all 10 choices or tries would lead to very unfortunate clustering results. So this is the way you can do by increasing the number of tries, right? And so when you use it in scikit-learn, the Python library that we are going to use for clustering in the next session, you will notice that there is a parameter. It will ask you, K-means will ask you, how many clusters should I find in data? And the second question that it will ask you is, how many times should I try to find clusters, right? So that it will look into the WSS and try to pick the best and so on and so forth. So number of tries matters. And so are we together? So that is for k-means clustering. I believe, oh, all right, it's already 1.5 hours. So we probably cannot cover all of this in one day. So you know what, today I'll stop with one algorithm because each of these are conceptually big. How about this? We repeat this and I will early release the code for this clustering so that even before the next time's lab, you guys can review the code, try to read it on your own, and then I'll walk you through this code next time. Right. But so clustering is a very beautiful thing. It's a beautiful algorithms in clustering. To find clusters in data has amazing, amazing scientific value. It is heavily used in medicine, in medical fields, medical research. It's heavily used in, I mean, I can't think of any field that does not extensively use it nowadays. And so we learned one particular algorithm, which is the k-means clustering. Okay. So any questions, guys?
Hello, sir. So here about the clustering, what you told us. So you mean to tell the number of tries will give us the more accurate clustering model? So like, because you told that when we are working on this clustering, it will ask us like how many clustering we need to find. So for example, if you press something like 10, I'm not sure. So that shows that there are 10 clustering and will be, I mean, the result will be more accurate.
No, 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 no. See, you mix up the number of tries with K. Don't do that. A K is asking how many clusters should I find? Let us say that you always want to find 2 clusters. But you realize that when you're trying to find 2 clusters, you might end up doing very well one time and not doing so well the next time, right? So what happens is you need a way to find out how good was your clustering, and you can use it to just, you know, try it a few times to make sure, maybe 2, 3 times to make sure, and pick the best clustering that you achieve for k is equal to 2. But the question still remains, what is k? What is the correct number of clusters? This algorithm, k-means clustering, is silent on that question. It doesn't answer that question. It says you have to tell me how many clusters there really are in the data. If you tell me how many clusters there are, I'll find it for you. And if you make a mistake, if you say, suppose there are 2 clusters, cows and ducks, right? So here, suppose you give me an answer like 5 or 3. I will find you 3 clusters and the best possible 3 clusters in the data. And then don't come blame me because you said 3 or you said 5. But I'll give you the best 5 clusters. That's what k-means clustering is saying.
So, sir, if we have data like in circular peripheral, means into circular ways, the data is distributed. So,
Right.
so in that way, this K means able to find the like
Centroid.
cluster.
Yes, yes, very well. So it's a good point you raised, Rahul. When the data, what you call circular, you can the people use fancier terms when the data has a convex, well-defined convex hull, or when people have a data is very convex, or I use a simple term globular, circular-like, right? For example, an ellipse will do just fine, isn't it, Rahul? Doesn't have to be circular. An ellipse could be. So a more general definitions are globular, roundish, some form of roundish or convex shape. When it is convex, k-means clustering works wonderfully. It is it does a very good job. The trouble with k-means happens when the data is not globular or when the 2 clusters overlap. Right. So with cows and ducks, it's easy. But what if you're talking about cows and buffaloes? you realize that there would be a certain degree of overlap, right, between the two clusters. Or cows and lions. So those are the situations where it becomes a little harder to tell whether a data point you should put, which cluster it should go into, and so forth. Right? So those are some of the limitations of k-means. And the biggest limitation is it answers half the question. You have to tell it how many clusters to find. Once you tell it that is the k, then it will go find it for you. But it's amazingly simple. Actually, if you think about it, I wrote down just 3 steps, or 2 real steps, 2 and 3 here. Assign each point to the nearest centroid, and then find the cluster associated with that centroid, and then repeat the process. It can't get simpler than that in machine learning. This is perhaps one of the simplest algorithms, and yet also an extremely powerful algorithm. Right? Both simple and powerful. It is one reason you find this used extensively in the industry, very, very commonly used in all sorts of problems in the industry. Right? And as I said, there will be clusters in your data, most likely. Right? And this answers that important question. How do you find those? So you can say that k-means is a clusterer. Right? K-means cluster is what we studied. And the process of finding clusters is called clustering.
Sir, one more doubt I have, sir. So you told that depending on the model, for example, if I tell I have found some 3 clustering, then if my friend, she tells that she has some 5 clustering, so then how will come to know that it is a correct model? So like we doesn't know the accurate clustering, right, in particular model, because my guessing may be 3 and her guessing may be 2. And finally, what will be the correct cluster in that case?
The answer to that is, and that is something I'll tell you about. Okay, maybe I should do that. It's a little techie. I mean, if you get it, it's all right. If you don't get it, it doesn't matter. Remember, I told you this WSS measure. What you do is this method is called the elbow method. Elbow method. What it says is for each of the value, k is equal to 2, k is equal to, even k is equal to 1, k is equal to 2, k is equal to, 3, 4. You can keep going, right? 5, 6, 7, 8, 9, 10. You can keep. What you do is you find the WSS, this measure that we talk about. And then when you do that, then you end up with a plot. Like for 1, you'll get a certain value. For 2, you'll get a certain value. For 3, you'll get a certain value. For 4, you'll get a certain value. For 5, you will now get a certain value. 6, certain value. So what happens is these values will still go down, keep going down, down, down. But you notice something interesting at this point. If you think of this as your hand, imagine that this is your shoulder and this is your hand. What is this? This is your elbow, isn't it? If you imagine your hand being like this, I don't know, are you getting the impression? So imagine, I won't make such a big hand. Let's say that this is it. These are your fingers. These are your fingers. I'm not a great artist. Imagine that this is your hand with your muscles and so forth. What is this point? It's your elbow, isn't it, guys? Are we seeing the intuition here?
Yes, sir.
Yeah. So what happens is if you look at the WSS plot, you will usually find an elbow at some point. And that elbow, wherever that elbow is, let's say its here is pointing to 4. So you would say that the best number of clusters to find in the data is 4. Right. So there is this elbow method. There's a more formal name, mathematical name, scree plot. Right. You can remember the scree plot if you want to, or more intuitively, just think of it. It is called the elbow method in common language. In more formal literature, you call it the scree plot. Right. So this is it, and you can plot it and just look for the elbow, and that will tell you between you and your friend which is the better answer to pick. 3 or 5 that you gave the example. Does that answer your question?
Yes, sir. Thank you.
That's that. All right, guys. So that is it. If you have any more questions, you can ask me. Otherwise, we'll call it a day. I hope you found this topic interesting. It's a very beautiful topic, clustering, and the algorithms here are very, very nice. Well, just remarkably powerful and simple algorithms.
So in the previous session, you had given us some homework regarding that one hot coding. So we need to find what exactly is that.
Yeah, one hot coding. And did you do that?
Actually, I was not sure with that, but I think it is something related to binary number 0 and 1, where all the coding will be taken to 0, 2, and 1. 1
No,
being the higher bit.
no, okay. One hot encoding. So, all right. So let me answer your question. One hot encoding. So suppose, there is a feature, xi, whose values are, let's say that you're looking at the ice cream, go back to your problem of sale of ice cream on the beach. Then your features are temperature. This is your x1. X2 is wind speed. Right? But x3 is day of the week. Day of week. Right? So your numbers would be, here would be a number. For example, this is 21 degrees. Wind speed is 17 miles an hour. But this could be like Tuesday, right? Wednesday, Sunday, right? Then maybe Monday, something like that, the values. So what do you notice? And then you have to predict here, the Y is ice cream sale of ice cream. Are we together? This is also a number, let's say 150 buckets, right? 152 buckets. Sunday will be 300 buckets. Monday is 140 buckets or things like that. So now the problem is when you try to put it into your algorithms will protest because it will say, well, you know what, we don't deal with textual. These values are not okay. These are strings. These are characters. These are not numbers. Math only deals with numbers. So how do we convert these things into numbers? We have a problem. So what you do is you actually do what is called one hot encoding. So this x3 is problematic. Why? Because at this moment, x1 belongs to real, x2 belongs to real, but x3 does not belong to real. So the way you solve this problem is you say, all right, I'm going to create binary features. I'll say, is Sunday, is Monday, is Tuesday, and so on and so forth, is Saturday. I created these 7 features. And so what will happen is for any given data, let's say that this is data 1, 2, 3. Let's look at the first row of data. Which of these values will be true? This is Tuesday, right? I put a 1 here, 0, 0, 0, 0, right? And then let us say for the third data set, I would have, it is a Sunday, right? So it would be 1, second data set would be Wednesday. So here we go, is Wednesday, right? So here 1, 0, 0, 0. For the third data set, it seems to be Sunday. 1 0 0 0 0, etc. You get the idea, right? So now what has happened is this 3 has become multiple variables. Let me call it x3, x4, x5, x6, x7, right, and so forth, and so on and so forth. Right now, now these values, are they numbers? They certainly are numbers, right? They're 0 and 1. Do you see that?
Yes, sir.
Yeah, and this is called one hot encoding, because now instead of a 3-dimensional space of input, the third one breaks up into 7 parts. So it becomes 7 plus 2. So you will end up with the input space now, x vector belongs to a 9-dimensional space, 2 of the dimensions being temperature and wind speed, and the other 7 dimensions being the one hot encoding. Is Sunday, is Monday, is Tuesday, is Wednesday, is Thursday, is Friday, is Saturday. Yep. 7 of those. And so this now is a number, and now you can continue on with your machine learning. So that is the meaning of one hot encoding.
Yes, sir. Thank you.
That's the meaning of it. I'll stop the recording now.
I have a question on regularization. Can I ask?
Of course, you can ask.
Actually, in regularization, we are adding penalty to the cost function, right? So, in the lasso regression, how it will eliminate some features?
1 second. So, please, what you are saying is regularization. Repeat your question. I'm sorry, I was a bit distracted.
In regularization, we are adding the penalty to the cost function, right?
That is one way of doing it. In your book, the 2 regularization methods that I mentioned, Ridge and Lasso, both of them add penalty terms to the loss function.
Yeah.
Is one way. There are many ways of doing regularization, by the way. That's not the only way, but those are the common ways.
Yeah. In the lasso regressions, we are adding absolute magnitude of coefficient.
Yes.
But how it will use it for the feature selection?
No, don't think of it like that. Lasso is unique regularizer because what it does is, and there's a beautiful geometry associated with it. The book talks about that. See, it's a little advanced for this class because there are people in this class who are from non-computer science, non-math background. So I didn't teach it, but the basic thing is this. Lasso is unique in the sense that it throws away some of the features. And so it helps you do dimensionality reduction by limiting your analysis to only a few features, a few dimensions.
Yeah, how it will make some feature elimination, like I read somewhere like it's the feature spaces will make it as a 0.
That's right.
Something.
It does that is see, it has to do with, now I'll have to talk about the geometry of loss function and so forth. How much do you know? Like, where should I start? Do you understand the shape of the loss function?
Yes, yeah.
Yeah. So you understand that. Okay. So then I can explain to you the answer to that. 1 second. I'll bring back my writing board again. All right. Let's try a luck here. See, what happens is, suppose you have, I'll take the world of 2 features, x1, x2, right? Okay. What happens is that the loss function will form contour lines, right? It will form, suppose the absolute minima of the sum squared loss is here, right?
Yeah.
What happens with loss function is the way the regularization just says, don't find the absolute minima, which is at point, let me just say A, right? Instead, take a less than the best minima. Don't find the absolute best solution. Find the best solution that you can possibly find within a region like this. Are we together?
Yeah.
And when you do that, so you know the story in Ramayana of Panchvati, Ram and Sita and Lakshman. They are in exile. Yeah, Vanvas. They are in there, and
Yeah.
so there are a lot of dangers in the forest. So Lakshman draws a Lakshman Rekha and tells Sita, "Don't step out of this magic circle."
Mm.
Right? And of course, the
Yeah.
entire story is that she, out of compassion, she ends up stepping out to give arms to this Ravan, the demon, and who ends up taking her away, whisking her away. So that somewhat like that. Think of this region that is in here. You basically set a region around the origin and say that whatever the solution is, I must find it within this sort of Lakshman Rekha. It is within this region of acceptability. One word people use it is that this is your constraint region or constrained region or the constrained surface. So then what happens is if you can find the answer only here, the best answer that you can find will be, if you really think about it, it'll be at this point, uh, at this point, right? Because any other contour, any other solution that goes into the region, these are contour lines, you know, these little circles. So each outer circle is the loss is more than the inner circle. So it's a not lesser solution. A is the absolute best solution. But if I tell you A is not acceptable, you need to find the solution within the constraint region, then this yellow point is the best point you can come to. Isn't it?
Yeah.
But now look at yellow very carefully. What does that yellow point says what? What is the value of x2? At the yellow point, what is the value of x2?
0.
0. So suppose x2 was the weight of the cow or weight of the animal. What have you just found? You said that in the
Weight is 0.
optimal solution, yeah, the weight doesn't matter. It's 0.
Yeah.
That feature has gotten eliminated.
Okay, got it.
That's the intuition behind Lasso doing a dimensionality reduction. Because you tend to, you know, these are these pointy edges. You end up puncturing the lost surface, right?
Mm.
At one of those pointy edges, you're much more likely to. And when you're more likely to puncture it at the pointy edges, those pointy edges are sitting on the axes. So it means that some feature values are 0 at that point. And that's how you get dimensionality reduction.
Okay. Oh, thanks, Asul. Yeah, I got a clarification.
Nice. Any other questions, guys? If not, then I'll close this meeting. Prabhat and Ravi,
Yeah.
Murli and Suresh, please stay back.
Thanks.
Thank you, sir.
You're welcome.
Thank you, sir.
Thank you.
Thank you.
Yes, if.
Are you guys benefiting? I've taken Prabhat, I remember, and Murli, I don't know if Murli was there. You were there first time I gave this workshop way at the time in Evolve, I believe. You remember that?
No, I was not there.
So you are listening to this for the first time, is it?
First time, yes.
Are you finding this useful? Are you finding this easy to understand?
Yeah, definitely.
Yes, also.
Very.
Concept is pretty much clear and easy. Relation is very simple.
Murli?
I can
Sound is
easily
echoing.
understand it.
Murli.
Oh gosh,
Now,
I can't hear a thing from you guys.
Murli, your sound is echoing.
how about now?
Not
Still,
good.
No.
Hello. Is that okay?
No.
No.
no, Murli.
Maybe I'll reconnect again.
Yes, if it is really useful, and I think we are getting a lot of the things clarified. And the one you explained now, the last function that how we, that is also, I couldn't find it anywhere, but yeah, I found it clarified. The guy asked the question, yeah,
Hmm.
clarified me as well, yeah, how
Good.
they are
Am I
derived.
audible now?
Not clear, Mulli.
Yeah.
Some issue with my let me
To do that book, guys, it's a very elementary book. It's the kindergarten of machine learning. But if you don't do that book, you know, thoroughly, and if you don't have every single line of that book in your mind, then you really will have a bit of a struggle in this field. That book was deliberately written to be the doorway to this field.
Yes, you said you are going to release the code for the K-means clustering. Some.
Yeah, yeah, I'll release it.
Asif, this one hot encoding, you said like the main purpose of that, like let us say we can also put like 1, 2, 3, 4, 5, 6, 7, right? For
No, no,
Sunday,
you
Monday.
No,
can't.
1, 2,
The
3, 4,
moment
5, 6, 7 will not work.
you
No, no,
can't.
I'm telling you, yeah. So the main purpose is like because if we put 1, 2, 3, 4, 5, 6, 7, it will count the weightage. So for that purpose, we
That
do
is
one hot,
that
right?
is the main reason.
Yeah,
Because the
yeah.
moment you put, see, in math we talk of the ordinal order.
Hmm.
Yeah? Those are ordered numbers.
Right,
Because
yeah.
there is an order, 4 is more than 3,
Yes,
and that
yes.
is the problem. You want to keep it as just binary, either
Yeah,
is
right.
or is not.
Yeah.
Nice, guys. Anyway, just wanted to do a check with you guys if you're benefiting from this.
Yes, Asif, we are benefiting. Means
Yes.
at least I went through the book earlier, but yeah, now it is like more clear for us.
Yeah, good. All right, guys. And then you
Yeah.
are the data science, you are part of the data science team, so you better pick this up over time. It will come to
Yeah.
you. See, machine learning is, my view, the easiest part of computer science because it's analytical. So there are no bugs. You know, you just reason through and you're done. You're not writing a very complicated user interface code in which when you click this button, maybe something else will happen that you didn't expect. So, good guys, I'll let you go.
Okay, Asif.
Thank you.
Enjoy the rest of your Sunday.
Best.
Yeah, bye.
Bye bye.